At 23 seconds past 1:23 in the morning on April 26, 1986, an engineer at a nuclear power station in the north of Soviet Ukraine pressed a button to shut his reactor down. It was a safety button. Its entire purpose was to stop the nuclear reaction, to drop the control rods, calm the core, end the test, make everything safe. He pressed the button that was supposed to save the reactor, and the reactor exploded. Not because the button failed. The button worked exactly as it was built to work. The reactor exploded because of the way that particular reactor was designed, because hidden inside its physics was a number, a coefficient, and that coefficient had the wrong sign. In almost every reactor ever built, a certain feedback runs in the safe direction. When the core gets too hot, the reaction naturally slows. In this reactor, under the exact conditions in the room that night, that feedback ran backward. The hotter it got, the harder it pushed. And the safety button, for the first fraction of a second, pushed in the wrong direction too. Within 4 seconds, the most powerful reactor accident in history had begun. This is the story of the equation with the wrong sign. To understand what happened at Chernobyl, you have to understand one strange and unsettling fact about a nuclear reactor. A reactor is not a thing that simply burns. It is a thing you have to argue with, continuously, forever, to keep it from running away. At the heart of a reactor is nuclear fission. A heavy atom, uranium, is struck by a subatomic particle called a neutron, and it splits. Splitting releases energy, which is the point. But splitting also releases more neutrons. And those new neutrons can go on to strike other uranium atoms and split them, releasing energy and yet more neutrons, which split more atoms. This is the chain reaction. It is the central idea of all nuclear power and all nuclear weapons. One split causes more splits, which cause more splits. Now, the entire question of whether a reactor is a useful machine or a catastrophe comes down to a single number. On average, when one atom splits, how many of the neutrons it releases go on to cause another split? If, on average, each split causes exactly one further split, the reaction holds steady. The power output is constant. Engineers call this critical. A reactor running at steady power is exactly critical. If each split causes less than one further split, the chain dies away. The reaction fades. The power drops. But if each split causes more than one further split, even slightly more, then the reaction grows. Each generation of splits is larger than the one before. The power climbs. And if it grows in an uncontrolled way, the power does not just climb, it runs away, exponentially, doubling and doubling in fractions of a second. A reactor, in other words, lives on a knife edge. Just below the edge, the reaction dies. Just above it, the reaction explodes. The whole craft of running a reactor is staying balanced, precisely on that edge. So how do you stay on the edge? How do you argue with a reactor? You use two main tools, and you have to understand both, because both of them matter on the night of the accident. The first tool is control rods. A control rod is a rod made of a material that is extremely good at absorbing neutrons, swallowing them, taking them out of the chain. When you push control rods into the core, they soak up neutrons, fewer splits happen, and the reaction slows. When you pull the rods out, more neutrons survive to cause splits, and the reaction speeds up. Control rods are the brake, and in a sense, the accelerator. The second tool is more subtle, and it is the true center of this story. It is called the moderator. When uranium splits, the neutrons it releases come out moving extremely fast. And here is a deeply counterintuitive fact. Fast neutrons are not very good at causing the next split. To reliably split another uranium atom, a neutron needs to be slowed down. The moderator is the material that slows the neutrons down. It does not absorb them, it just slows them so they become good at causing splits. Without a moderator, the chain reaction in that kind of reactor would weaken and stall. The moderator is what keeps the chain alive. The reactor at Chernobyl was a specific Soviet design, and its name was an acronym, RBMK. The RBMK was a large, powerful reactor, and it had been built across the Soviet Union because it had real advantages. It could be refueled while running, and it could be built very large, producing an enormous amount of electricity. But the RBMK made two design choices that, combined, created a hidden flaw. And to see the flaw, you have to know what the RBMK used for its moderator and what it used for its coolant. The moderator, the material that slowed the neutrons, was graphite. Solid blocks of graphite, the same substance as pencil lead, stacked into an enormous mass with channels running through it. And running through those channels was the coolant, ordinary water, pumped through to carry away the heat and, by boiling, to drive the turbines that made electricity. So in the RBMK, the moderator and the coolant were two different substances. Graphite did the moderating, water did the cooling. And that separation, graphite for one job, water for the other, is the seed of the entire disaster. Here is why having a separate graphite moderator and water coolant is dangerous. And this is the technical heart of the episode, so let me build it carefully. Think about the water flowing through the core. It has two effects on the chain reaction, and they pull in opposite directions. On one hand, water absorbs some neutrons. Not as strongly as a control rod, but it does soak up a fraction of them. So the water, just by being there, is gently slowing the reaction down, acting a little like a brake. On the other hand, the water is not the moderator. The graphite is. So the water is not needed to keep the chain alive. The graphite handles that. Now ask the critical question. What happens if the water gets hotter and starts to boil and turns to steam? When water boils, it becomes steam, and steam is far less dense than liquid water. There is far less actual substance in a given space. A bubble of steam is, compared to liquid water, almost empty. So when water in the core boils into steam, you have effectively removed water from that part of the core. The voids, the steam bubbles, are gaps where water used to be. And here is the trap. The water was the thing gently absorbing neutrons. The graphite, doing the moderating, is untouched. It is still there, still slowing neutrons, still keeping the chain alive. So when the water boils away, you lose the brake, but you keep the engine. You remove neutron absorption, and the moderation continues. And so the reaction speeds up. That effect has a name. Engineers call it the void coefficient. The void coefficient is a number that answers one question. When voids, steam bubbles, form in the core, does the reaction speed up or slow down? If forming voids slows the reaction down, the void coefficient is negative. And negative is safe. It means that if the core overheats and the water boils, the reaction naturally calms itself. Boiling acts as a brake. The reactor is, in this respect, self-stabilizing. Most reactors in the world, including almost all Western power reactors, are designed to have a negative void coefficient. It is considered a basic principle of safety. But the RBMK, because it used graphite to moderate and water only to cool and gently absorb, had a void coefficient that was positive. Forming voids in an RBMK sped the reaction up. Boiling in that reactor was not a brake. Boiling was an accelerator. The sign of that coefficient, positive instead of negative, is the wrong sign in the title of this episode. And under the conditions of that night, that sign would turn a routine test into the worst reactor accident in history. The accident at Chernobyl did not happen during normal operation. It happened during a test. And the test itself was, in its intention, a genuine safety improvement. So it is worth understanding clearly. A nuclear power station, even when its reactor is shut down, still needs electricity. It needs to keep its coolant pumps running, because a reactor that has just been shut down is still extremely hot and must keep being cooled for a long time afterward. Normally, that electricity comes from the reactor itself or from the external power grid. But what if the reactor trips offline and the external grid fails at the same moment? Then the pumps would stop and the core could overheat. The station had emergency diesel generators for exactly this situation. But the diesels took about a minute to start up and reach full power. And a minute for a reactor's cooling is a dangerous gap. So engineers wanted to test an idea to bridge that gap. When the reactor's steam supply is cut off, its turbine does not stop instantly. It keeps spinning, coasting for a while on its own momentum. The test asked, could that coasting turbine, in its dying spin, generate just enough electricity to run the pumps for that one critical minute until the diesels came online? It was a sensible question. It had been attempted before without full success. On the night of April 25th into the 26th, 1986, they were going to try it again. To run the test, the reactor's power had to be lowered. The plan called for the reactor to be brought down to a reduced power level where the turbine coast-down test could be safely performed. But the test was repeatedly delayed. The regional electricity grid needed Chernobyl's power that evening, and the controllers were asked to hold the reactor at higher power for hours longer than planned. This delay matters because it meant the test was finally carried out late at night by the night shift, a crew that had not necessarily planned or trained for this specific test, taking over a procedure already behind schedule. And then, while lowering the power for the test, something went wrong with the reactor itself. The power, instead of settling at the intended reduced level, fell much further than planned. It plunged, dropping to a very low level, almost nothing. And a low-power RBMK is, it turns out, a particularly treacherous machine. The crew, behind schedule, under pressure, and now facing a reactor that had nearly stalled, made a decision. Instead of shutting down and starting fresh, they tried to recover the power and continue the test. To pull the power back up from that near stall, the operators did the only thing that would work quickly. They withdrew control rods. A lot of them. Far more than the operating rules permitted to be withdrawn at once. Remember, control rods absorb neutrons and slow the reaction. To raise power from near zero, the operators pulled rods out of the core, removing absorption, letting the chain reaction build back up. They managed to stabilize the reactor at a low power level. Enough, they judged, to run the test. But the core was now in an extraordinarily dangerous state, and the operators could not fully see it. With most of the control rods pulled out, the reactor had almost no margin left. The brakes were nearly all the way off. And in this fragile, depleted, barely controlled condition, a state the reactor should never have been allowed to enter, they began the test. They cut the steam to the turbine and let it begin its coast down. And the positive void coefficient, which had been waiting silently inside the physics of the machine the whole time, was handed exactly the conditions it needed. So now we reach the question at the heart of this whole story. How does pressing a safety button, a button designed to shut the reactor down, cause that reactor to explode? To answer that, I have to bring together two ideas: the positive void coefficient, which we have built up carefully, and a second, almost unbelievable flaw hidden in the control rods themselves. Let us take the void coefficient first, in the conditions of the test. The turbine has been cut off, and as a result, the pumps feeding the core begin to slow, and the flow of cooling water through the core decreases. Less water flow means the water in the core heats up more and begins to boil more. More boiling means more steam voids. And the void coefficient was positive. More voids means a faster reaction. A faster reaction means more heat. More heat means even more boiling. Even more boiling means even more voids. Even more voids means an even faster reaction. Do you see the shape of it? It is a loop, a self-feeding loop. Boiling causes power, and power causes boiling. This is a positive feedback loop, and a positive feedback loop is one of the most dangerous things in all of engineering. In a stable system, feedback is negative. A change triggers a response that opposes the change. Push it, and it pushes back toward where it was. But in a positive feedback loop, a change triggers a response that amplifies the change. Push it, and it pushes itself further in the same direction. The RBMK at low power, with the water boiling, had become a positive feedback loop. A small rise in power caused boiling, which caused a larger rise in power, which caused more boiling. At that point, the reactor was no longer something the operators were arguing with. It was something that had begun to argue with itself, and win. The power in the core began to climb, and because the feedback was positive, it did not climb gently. It began to accelerate. It was at this moment, with the power beginning to rise, the operator seeing it, alarmed, that someone pressed the button. The emergency shutdown button. In the RBMK, it was called AZ5. Its job was to drive every single control rod fully into the core, all at once, slamming the brakes on the entire reaction. It was the right instinct. It was the thing you are supposed to do. But here is the second flaw, the one hidden in the control rods. And it is genuinely difficult to believe. The RBMK control rods were not made of a single material. The main length of each rod was the neutron-absorbing material. Good. But the very tip of each rod, the bottom end, was made of graphite. And graphite, remember, is the moderator. Graphite speeds the reaction up. So picture a control rod that has been almost fully withdrawn from the core, sitting up near the top. Below the absorbing part of the rod, in the channel, there is its graphite tip. And below that, water. When that rod begins to drop, the first thing that enters the core is the graphite tip. The graphite tip pushes downward into the channel and displaces the water that was there. It replaces neutron-absorbing water with neutron moderating graphite. So for the first few seconds of insertion, in the lower part of the core, the control rod, the safety device, the brake, actually speeds the reaction up. The crew pressed the button to stop the reactor, and the button, for its first terrible moment, did the opposite. So let us actually write down the equation, or rather the central relationship, that destroyed the Chernobyl reactor. At the heart of reactor physics is a quantity called reactivity. Reactivity is, in essence, the measure of how far the reactor is off the knife edge. If reactivity is exactly 0, the reactor is critical, steady, balanced, constant power. If reactivity is negative, the chain reaction is dying and the power is falling. If reactivity is positive, the chain reaction is growing and the power is rising. So the single most important equation in this story is conceptually simple. The rate at which the reactor's power changes depends, above all, on the reactivity. Positive reactivity, power climbs. The larger the reactivity, the faster it climbs. The whole question of that night is one question. What was the total reactivity of the core, and was it positive or negative? Now, the total reactivity is not a single thing. It is a sum. It is a sum of contributions, and several different effects each add their own term to it. And the two terms that matter for Chernobyl are the two we have built up. There is the void term, the contribution to reactivity from steam voids in the core. Because the void coefficient was positive, when the water boiled, the void term added positive reactivity. Boiling pushed the sum toward runaway. And there is the control rod term, the contribution from the control rods. Normally, inserting rods adds a large negative reactivity, pulling the sum down toward safety. But because of the graphite tips, in those first seconds of the emergency insertion, with the rods starting from nearly fully withdrawn, the control rod term did not start negative. It started positive. The insertion of the rods for that initial moment added positive reactivity instead of removing it. So look at the sum at the instant the button was pressed. The void term, positive, and growing as the water boiled harder. The control rod term, which should have been a large negative rescue, was instead, in that moment, also positive. Both of the terms that were supposed to be able to save the reactor were, at that instant, pushing the same way. Both were adding positive reactivity. The sum did not go negative. The sum spiked upward. Now I need to make one more idea concrete, because it is the difference between a reactor that surges and a reactor that detonates. When the total reactivity becomes strongly positive, the power does not just rise. It rises on a curve that doubles, and then doubles again, and then doubles again, faster and faster. Exponential growth. And the speed of that growth depends on how positive the reactivity is. A slightly positive reactivity gives a slow, manageable rise that operators can catch. But a strongly positive reactivity, a large spike, gives a rise so fast that no human being and no mechanical system can respond in time. At Chernobyl, in those seconds, the reactivity spiked so high that the reactor went what physicists call prompt critical, a state where the chain reaction grows on the timescale of the neutrons themselves, a timescale of fractions of a millisecond. Once a reactor goes prompt critical, the outcome is no longer in human hands. The power climbs through millions of times its normal level in the space of a few seconds. The investigations later estimated that the reactor's power in those final moments surged to something on the order of 100 times its full rated output, and possibly far beyond, in roughly 4 seconds. The equation had run away, and the sum of those wrong-signed terms had carried it there. So let us go back to the control room at 23 seconds past 1:23 in the morning with the equation in hand. The operator presses the AZ5 button. The control rods begin to descend. The graphite tips enter the bottom of the core first. In the lower region of the core, reactivity spikes. The power, already rising from the void feedback, surges. The surge causes a violent, sudden burst of heat in the fuel. The fuel temperature climbs so fast and so high that pieces of the fuel begin to shatter and fragment. And shattered, superheated fuel dumped into the surrounding water flashes that water instantly into steam. An enormous volume of steam is generated in a fraction of a second, and the reactor was a sealed, pressurized system. The pressure inside the core spiked beyond anything the structure could contain. The first explosion was a steam explosion. The colossal, sudden pressure of the flashed steam blew the core apart and lifted the reactor's enormous upper biological shield, a circular slab weighing around 2,000 tons, up off the top of the reactor. And then, a moment later, came a second explosion. The precise nature of the second blast is still discussed by experts. It may have involved a further surge of nuclear power, and it certainly involved chemical reactions, hydrogen and other gases generated by the extreme heat and the shattered materials igniting. The second explosion completed the destruction. It blew apart the top of the reactor building, hurled chunks of the reactor core, fragments of graphite and fuel, intensely radioactive, out onto the roof and the surrounding ground, and tore open the building to the sky. The reactor was destroyed. The chain reaction had finally stopped. Not because it was controlled, but because the core that sustained it had been physically blown apart and scattered. The whole sequence, from the press of the button to the explosions, took roughly 4 seconds. 4 seconds. That is the speed at which an equation with the wrong sign runs. In the immediate term, the explosion and the fire it started killed and injured the people closest to it. 2 plant workers died very soon after the blast. In the weeks that followed, the firefighters and station staff who had been exposed to enormous radiation doses while fighting the fire and trying to contain the disaster began to die of acute radiation sickness. The official immediate and early death toll from acute radiation effects is generally counted in the dozens. But the explosion had also torn open a reactor core and let its contents burn in the open air. The graphite moderator caught fire and burned for days, and that fire lofted radioactive material high into the atmosphere. The contamination spread across the Western Soviet Union and into Europe. The nearby city of Pripyat, built to house the plant's workers and their families, was evacuated permanently. Tens of thousands of people left their homes and never came back. A vast exclusion zone was established around the plant, and it remains in place to this day. The full long-term health toll of Chernobyl, across decades and across populations, has been studied and estimated and argued over extensively, and the numbers vary widely depending on method and assumption. But by any honest accounting, the consequences of those 4 seconds reach far beyond the people who were in the building. The investigation into Chernobyl was long and politically fraught, and it went through more than one official version. The earliest Soviet account placed the blame almost entirely on the operators, on the crew who had violated procedures, withdrawn too many control rods, and run the reactor into a dangerous state. And it is true that the operators made serious errors that night. They did violate rules. They did push the reactor into a fragile, depleted condition it should never have been in. But over the following years, as international experts and a more honest later Soviet analysis examined the accident, the picture changed. The deeper conclusion was that the operators' errors had been catastrophic only because the reactor itself had fundamental design flaws. A positive void coefficient, control rods with graphite tips that caused a positive reactivity spike on insertion, a reactor that was especially unstable and treacherous at low power. The crew made mistakes, but the crew had been handed a machine that turned their mistakes into a detonation, and that, under the right-wrong conditions, would respond to its own emergency shutdown button by surging. And here is the detail that makes Chernobyl belong on this channel. The flaws in the RBMK were not unknown before April 1986. The positive void coefficient was a known property of the design. It was understood in principle by the physicists who designed and studied these reactors. The dangerous behavior of the control rods, the positive insertion spike, had actually been observed before. At another RBMK plant, at Ignalina in Lithuania, a similar control rod effect had been noticed during testing in 1983, 3 years before Chernobyl. The phenomenon had been seen. It had been written down. But that knowledge did not travel. It was not forcefully acted upon. It did not result in the reactors being modified or in the operators being clearly and urgently warned that their emergency shutdown button could, under certain conditions, do the opposite of what they expected. The equation was known. The wrong sign was, by 1986, sitting in technical documents and in the minds of specialists. What was missing was the institutional will to take that known equation, carry it to the people standing at the control panels, and act on it before the demonstration came. The mathematics did not fail at Chernobyl. The flow of the mathematics, from the people who understood it to the people who needed it, failed. What Chernobyl changed, it changed permanently and worldwide. After the accident, the remaining RBMK reactors were extensively modified. The control rods were redesigned to remove the dangerous graphite tip effect. The fuel and the operating rules were changed to reduce the void coefficient and make the reactors far less unstable at low power. The flaws, once they had been demonstrated in the most terrible way possible, were finally engineered out. More broadly, Chernobyl reshaped the entire global culture of nuclear safety. It led to the creation of new international bodies and standards for sharing safety information across borders, precisely so that a known flaw discovered at one plant could not stay locked in a drawer while other plants ran on. The concept of safety culture, the idea that a nuclear operation must actively, institutionally cultivate the habit of surfacing and acting on bad news, became central, in large part because of Chernobyl. The reactors were fixed, the reporting was fixed, the culture was forced to change. All of it written in the most expensive ink imaginable, in the aftermath of 4 seconds. Chernobyl is now, around the world, one of the most intensively studied accidents in the history of technology. It is taught in nuclear engineering as the defining lesson in reactor stability and the absolute importance of a negative void coefficient. It is taught in the study of complex systems as a model of how a positive feedback loop, once it crosses a threshold, escapes all human control. It is taught in organizational and management studies as the consequence of a culture that suppressed bad news, that placed schedule and authority above the honest upward flow of safety information. All of those readings are true. But here's the thing about Chernobyl that I find most haunting, and it is the thing that connects it to every other story on this channel. The disaster did not come from ignorance of the physics. When the Vasa sank, the equation of metacentric stability genuinely did not exist. It would not be written for another century. When the Tacoma Narrows Bridge fell, the equation of flutter lived in another field entirely, in aeronautics, and had not crossed the wall into civil engineering. But the physics of Chernobyl was not missing, and it was not in another field. The void coefficient, the reactor kinetics, the behavior of the control rods, all of it was nuclear physics, fully developed, written down, understood by the specialists who designed the very reactor that exploded. The equation was not late. The equation was not lost. The equation was complete and correct, and it had even, in the case of the control rods, already been observed misbehaving. What failed was everything around the equation. The decision to build a reactor with a known dangerous sign. The failure to carry a known flaw to the people at the controls. The culture that did not let the warning travel. The mathematics was right. The humans did not let it be heard in time. I want to leave you with the thought I find most sobering about Chernobyl, and it is the reason this story belongs on this channel. We tend to imagine that if we simply understand the equations, if the science is correct and complete, then we are safe. Chernobyl is the proof that this is not enough. The science was correct. The science was complete. The void coefficient was a known number with a known dangerous sign. And the reactor was built and operated anyway. Knowing the equation is not the same as respecting the equation. And respecting the equation is not the same as making sure that the person whose hand is on the button respects it too, and understands exactly what the button will do. The positive void coefficient did not care that somewhere in a Soviet physics institute its danger was understood. It did not care that the control rod flaw had been seen 3 years earlier at another plant. An equation is indifferent not only to our hopes, but to our private, undelivered knowledge. It does not run on what the experts know. It runs on what the system is actually built and operated to do. The deepest lesson of Chernobyl is that a known equation, locked in a drawer or trapped in a specialist's head, protects no one. The mathematics has to be carried all the way to the moment of action. Otherwise, the universe will, eventually, deliver the demonstration itself. And the universe charges a terrible price for the lesson. The fourth reactor at Chernobyl was, in the years after, sealed inside an enormous structure. First, a hastily built concrete sarcophagus, and later, completed in recent years, a vast steel arch slid into place over the ruin to contain it for a century to come. The other RBMK reactors were modified, and the worst of the design flaws were finally engineered out of existence. The reactor exploded because a coefficient had the wrong sign, and because the people who knew it did not, in time, make the people at the controls know it too. Strange equations are not always strangers. Sometimes the equation is fully known, sitting in plain view, with its dangerous sign clearly marked. And the catastrophe happens anyway, because knowing a thing and acting on a thing are separated by every weakness a human institution can have. The reactor's physics ran on schedule that night. It always would have. The only question was ever whether we would listen before it did. If you enjoyed this one, the story of how a great crowd of pedestrians, simply walking across a brand new bridge in London, fell unconsciously into step with one another and set the whole span swaying beneath them, a feedback loop made of human footsteps, is a story for another day. Strange Equations is here for the math behind the moments that nobody at the time was calculating. If that is your kind of channel, subscribe. Thank you for watching.